do you have like a pointer or something?
Yep.
Otherwise,
So it's a USB. So you can use one
Right,
now.
today we're very excited to have our own incoming postdoc. So Sari is going to join us in the fall, and for this week is visiting. So he's a PhD candidate at Stanford. He has been working with Peter Graham on important topics such as searching for ultralight dark matter, and he also studied inflation. Today he's going to tell us about Earth as a transducer for ultralight dark matter detection.
All right, great. Well, yeah, thanks for having me. Yeah, as Raymond said, my name is Sark. I'm here from Stanford, and I'm going to tell you about recent work with R.L. Arza, Michael Fetica, Peter Graham, and Derek Jackson Kimball on a novel way to detect ultralight dark matter using the Earth. So there are many existing shielded or cavity experiments, such as ADMX or DM radio, which are looking for ultralight dark matter through its coupling to electromagnetism. So these include models such as dark photon dark matter, which can turn into normal photons through its kinetic mixing with EM, or axion-like dark matter, which can convert into photons in the presence of some static background magnetic field. Now, one fact about these types of experiments that I'll get to in a bit is that the signal size scales with the size of the apparatus. So, if you have a bigger cavity, you'll get a bigger signal in general. In particular, in the dark photon case, this scaling usually appears as the mass of the dark photon times the size of the apparatus. So in particular, this scaling becomes really important when you get to very, very low mass dark matter. In particular, once you get below about like 10 to the minus 14 EV or so, then basically it becomes impossible to do anything in the lab. And basically all the constraints below that mass come from large astrophysical objects like gas clouds or dwarf galaxies. But the properties of such objects can sometimes be somewhat uncertain, and this can lead to some skepticism around those bounds. Luckily for us, though, there is one very large object, which we're all quite familiar with, and well, we're all standing on it, it's the Earth. So I'm actually going to tell you guys a way that we can use the Earth as our apparatus for detecting ultralight dark matter. In particular, we'll use it as a transducer. So a transducer is something that turns one signal of one type into another. So today, the Earth will be turning ultralight dark matter into some observable magnetic field signal at the Earth's surface. So as I mentioned, our setup is similar to shielded or cavity experiments like ADMX or DM radio. In such experiments, you usually have some vacuum region, which is surrounded by some conducting shield. And the purpose of the shield is to keep out normal photons, but it'll let dark photon or dark matter in general in. And if that dark matter couples to EM somehow, then that can turn into normal photons inside the box and give you some observable signal. In particular, usually the signal you'll get is some magnetic field, some oscillating magnetic field inside the inner walls of the box. In the case of the dark photon, this is basically the entire story, because the dark photon can get inside the box and just convert into normal photons on its own through its kinetic mixing. In the case of axions, you also need some static background magnetic field in order to get it to convert. But it's the same signal you end up getting. You'll get some oscillating magnetic field signal inside the box.
But isn't the B field used to scan the mass of the axion? Is that right? Because you won't have anything to scan for the Earth.
Yeah, well, I think in DM radio, the thing you use to scan is the readout is some LC circuit. And so I think they're scanning the resonant frequency of that circuit. And I think in ADMX, I believe that they're scanning like the physical shape of the cavity, I think changes the resonant modes. I think that the background magnetic field is static.
Okay, but there's a variable that scans over the possible axion masses. Is that right?
Good. Okay. So also, so that is in the resonant case. That's when you're like trying to match the frequency. Really, what I'm talking about here is the like low mass tails of these effects. So now I'm not really looking for a resonant effect here. So this is what it would look like if the mass of the or the Compton wavelength of the dark matter is much larger than the box. box.
Oh, I see.
Yeah. So we don't actually need to scan here. Good, yeah, but that's a good point. Yeah, so anyways, our setup is similar, except rather than using conductors in a lab, we use the natural conductors around us. So in particular, the Earth below us and the ionosphere interplanetary medium above us. For our purposes, these actually turn out to both be pretty good conductors. However, the lower atmospheric region where we're standing right now, this like inner region here is a relatively poor conductor. So that acts as the analog of the vacuum region. And so just like in the cavity case, what you expect to get is some observable magnetic field signal inside this lower atmospheric region at the Earth's surface. And that's something we can detect. Now, one important fact, as I mentioned about these shielded or cavity experiments, is that the signal size scales with the size of your box. Now, you might hear me say that and look at the picture on the right and become slightly worried because, well, we have 2 length scales in our setup. We have the very large radius of the Earth, but we also have this much shorter height of the atmosphere. And so you might say, well, Sarek, for all I know, maybe you're just suppressed by the shortest length scale. So maybe this is a tiny effect. You're not going to see anything. And one important result of our work is that actually you end up scaling with the much larger radius of the Earth, not the short height of the atmosphere. So this actually ends up being a big signal. And I'll show you where that comes from in a bit. So the outline of my talk will be roughly as follows. I'll start off introducing some of the basic physics of the dark photon and axion-like dark matter. And in particular, I'll introduce this effective current formalism, which is kind of a calculational framework which will unify both of them and make solving for the actual signal pretty easy in both cases. And I'll use that effective current approach to solve a particular toy example. In fact, it's going to be this cavity, ADMX or DM radio cavity that I showed you before, and I'll show you where the L scaling comes from. Then I'll move on to the actual Earth signal. So I'll start off by going through the conductivity environment in and around the Earth. And then if time allows, I'll go through a derivation of where the actual Earth signal comes from and then review some of its properties. And then finally, at the end, I'll talk about how we actually detect this signal. So as I mentioned, it's some magnetic field signal all across the Earth. So ideally, what you would want to detect this is some array of magnetometers distributed all over the Earth, taking data for many, many decades. And actually, it turns out that the hard work has basically been done for us already there, because geophysicists have been trying to measure the Earth's magnetic field for their own purposes for quite some time. So there's actually tons of publicly available data of magnetic field measurements all across the Earth. We use data from this SuperMag collaboration, and we actually undertake an analysis to set bounds on dark photon and axion parameter space. So I'll show you the results of those analyses as well.
So this SuperMag is geologists, that's what they said.
Yeah, geophysicists.
Geophysicists.
Yeah, it's a collaboration at Johns Hopkins APL. Great, and of course, yeah, if you have any questions, please feel free to ask. Great, so let's start off with some basic dark photon physics. So this is the Lagrangian for a kinetically mixed dark photon. There are a few different equivalent ways of writing this Lagrangian, so let me step through some of the properties of this way of writing it. First off, there are 2 modes, one which I'll call the interacting or maybe sometimes normal photon, and one which I'll call the sterile or maybe sometimes dark photon, A prime. And importantly, only the interacting mode actually couples to physical E&M charges. You can see that from this last term. So this means, for instance, if you have like some wall, say, then a normal photon will be stopped by the wall, but a sterile photon will go through the wall, no problem, at least to leading order. Also, the observable fields that you would actually detect from a magnetometer or an antenna or something are the ones associated with A, not with A prime. They have no contribution from A prime. You can see we have a mass term here. This is going to mean one of our propagation states is massless, like the usual photon you're familiar with, and one of them is going to be massive. In particular, we'll take this mass to be pretty small. But importantly, you'll note that because of this mixing term here, A and A prime are not actually the propagation states. So this is an analogy to neutrino mixing. You know, if you have some off-diagonal mass terms between your neutrinos, then this makes the flavor states not the propagation states for the neutrinos, so you can get some neutrino oscillations. So in particular, if you start with entirely interacting at some point in space, and you let your photon propagate, it might turn into mostly interacting with a little bit of stereo. You can see from this term in the Lagrangian that these mixing effects are all going to be proportional to the mass. Again, in analogy to neutrino mixing, you might know that if the neutrinos were exactly massless, you get no oscillation. So that's the same thing here. All of our observable effects which come from this mixing have to be proportional to the mass of the dark photon. This is the mass scaling I mentioned earlier. Now, everything I just said is true in vacuum. However, the story changes inside a conductor. There, A and A prime actually do become the propagation states. Again, in analogy to neutrino mixing, you might know that in a medium, the electron neutrino actually becomes a propagation state because it talks to the electrons more than the other neutrino flavors. So this creates a mismatch at the boundary of a conductor where you have A and A prime are the propagation states inside the conductor, but they're not the propagation states outside the conductor. And so this can lead to interesting mixing effects at the surface of conductors. And this is why this can be a good environment to look for effects of the dark photon. Good. Now, when the dark photon is the dark matter and you're taking the coupling to be relatively small, so you can neglect back reaction, then there's a relatively simple way of treating the dark photon. You can see by looking at these last two terms that actually the effect of a dark photon is precisely equivalent to the effect of some electromagnetic current. So we can just parameterize it by some effective current. In particular, since the dark matter is non-relativistic, we're going to take V to be exactly 0 for most of this talk. This means a few things about this effective current. One, the zero component is 0. This means there's no associated charge, it's just a current. It's also constant in space. This is true for the dark photon case, but in the axion case I'll get to in a second, this will be different. And it also means that the current oscillates with a frequency exactly equal to the dark photon mass. So you just have some constant current throughout space oscillating at a frequency m. And then once you parameterize the dark photon this way, then the problem is relatively simple. It just becomes a single photon E&M problem. This is something you could have done in like a graduate E&M class. Great, so now switching gears really quickly, I want to talk about some basic axion physics. So this is the Lagrangian for an axion-like particle. This is going to be some massive pseudoscalar. Again, we're going to take the mass to be relatively small. And it's going to couple to E&M through some AFF dual type term. And what this term does is it allows the axion to convert into a photon in the presence of some static background magnetic field. In particular, if you take the non-relativistic limit of the dark matter, then basically the only effect it has on Maxwell's equations is it just adds this additional term to Ampere's law. And if you're familiar with Ampere's law, you might know this is exactly where you might put a current term. So again, the axion just behaves precisely like some effective current, similar to the dark photon case. In fact, if you compare this formula to the formula on the previous slide, you can see that there's a quick replacement rule you can make. So if you have any dark photon effects and you want to translate them to axions, a nice easy way to do it is just to replace epsilon m with g times the magnetic field. That's usually a quick and dirty way of doing it. One important thing to note, though, is whereas in the dark photon case, the direction of this current was set by the actual dark photon polarization, now the direction is set by the magnetic field in question. So for instance, in the Earth case, the magnetic field we're going to be using is actually the Earth's geomagnetic field. So for instance, that will not be constant throughout space, whereas it was in the dark photon case. Okay, so how do we actually use this effective current approach? I'll go through a quick toy example, which is just going to be this cavity geometry that I introduced earlier. So let me take it to be a cylindrical cavity, so it looks like a circle from the top, square from the side, a rectangle. And for a second, I'll just consider the dark photon case, and I'll consider the case where the dark photon is polarized along the cylindrical axis of the cavity. You can do a similar calculation for the axion case. If you take the B field to be polarized along the cylindrical axis of the cavity, it'll be basically the same result. And so now I'll use this effective current approach to show that our signal indeed scales with the size of the box, but in particular, it's actually going to scale with the transverse direction R, not with this longitudinal direction L. And even if L happens to be much smaller, so even if this is like a pancake, shaped cylinder, you'll still scale with the larger the larger length scale. So it's not always the shortest length scale that you're suppressed by. So we can derive this scaling pretty easily just using Ampere's law. So let's consider some Amperian loop, which runs just inside the cylinder, like just around the cylinder. As I said, the dark photon can be parameterized by some effective current. And Ampere's law tells you that if there's some effective current running, or if there's some current flux running through your loop, then that corresponds to some magnetic field around the perimeter of the loop. If you do some just basic scaling, just to see how this magnetic field scales, then the Ampere's law tells you the magnetic field times roughly the radius of the, or the circumference of the circle will go like the area of the circle, r squared, times the effective current, epsilon m squared a. Then shuffle things around and put it in terms of the actual dark matter density, and you'll see that the magnetic field sourced by a dark photon is has precisely this MR scaling that I've been telling you about. And in particular, the R here is this horizontal direction here, not the longitudinal direction L. In particular, you can see that I really could have put this Amperian loop anywhere in this vertical direction that I wanted, and my argument would have carried through exactly the same. So this argument doesn't really care about this vertical direction at all. It only cares about this R. So even if L is pretty small, you still get a big signal.
But that's because the perimeter is dominated by L.
Yeah, exactly. Yes, yeah. Yeah, and again, a similar calculation goes through. If you take the axion case, you can convert using the quick rule I told you, epsilon m just goes to GB. But again, you still get this R scaling. Cool. So now we can start talking about the actual Earth signal. And so to start off this discussion, I want to talk about the conductivity profile in and around the Earth. But before I get to that, I just want to quickly think about what actually makes a good shield. I've been talking about these shielding walls. What are the criteria for things to actually be a good shield? So there's the one perhaps more obvious condition, which is just that it needs to be a good conductor. In fact, we'll also be thinking about plasmas. So if it has either a high conductivity or a high plasma mass, in the case of a plasma, then it will be a good conductor. But there's an additional condition, which is you actually need to be sufficiently thick in order to shield the entirety of the incoming signal. You know, like a piece of tinfoil is not going to stop a lightning bolt. You need some thickness to it. So in particular, these are the corresponding damping length scales inside a conductor or a collisionless plasma. And we want to make sure that our layer is thicker than either of these damping scales. Good. So now I'm going to briefly walk through some of the different layers in and around the Earth. And I'm going to throw up, this is sort of a schematic diagram here, but I'm going to throw up some rough numbers down here as well. The exact numbers aren't super important. This is just to give you a sense. But the important thing to look for are the two conditions I told you on the previous slide. A, is the conductivity or plasma frequency bigger than whatever the dark photon mass we're considering is? Take that to be roughly like 10 to the minus 18 eV or something. And is the layer thicker than the damping length scale inside the layer? Okay, so first off, we can start with the Earth itself. I'm showing you numbers here for the core. You can see the core is very conductive. It has iron and stuff in it. It's also quite thick and has a pretty short damping length scale. So indeed, the core is definitely an effective shield. It won't let any like signals through it. Then we get to the lower atmosphere. The lower atmosphere has a very low conductivity. It's actually kind of close to the masses we're talking about. But if you look at the damping length scale, that's way, way, way larger than the thickness of the atmosphere. So indeed, the lower atmosphere is not going to be a good shield. We can treat that as a vacuum. Next, we get to the ionosphere, and this is where things get a little bit complicated. So the ionosphere is the upper layer of the atmosphere, which is highly ionized. People tend to treat it as a good conductor for a lot of purposes. For instance, it's useful for like AM radio propagation. But in our cases, things get a little tricky because the ionosphere is actually an anisotropic conductor. The Earth's magnetic field runs through the ionosphere, And electric charges like to follow magnetic field lines, so it conducts much more efficiently along the Earth's magnetic field than it does perpendicular to it. So if you look at the numbers for the parallel conductivity, you would think it is a pretty good shield. It's much larger than the corresponding damping length scale. But if you look at the numbers for the perpendicular conductivity, then it's less certain. So the effect of the ionosphere in our case is actually quite complicated, and it's a little bit uncertain, but I'll get back to this in a second, what we actually do about this. But then finally, if you go even further out, you go to outer space, the interplanetary medium. This actually acts more like a collisionless plasma than it does a conductor, but indeed it ends up still being a very good shield. In particular, like the length scale I'm showing here is like the Earth-Moon distance, but you can see that's way, way, way longer than the corresponding damping scale in the ionosphere or in the interplanetary medium. So the interplanetary medium is definitely a good shield. So in summary, we have the Earth is a good shield, lower atmosphere is a bad shield, ionosphere is a little bit unclear, and then we have outer space past that is definitely a good shield. So in our work, we kind of take two different approaches for how to actually model this system. One is to consider the ionosphere to be a good shield and just take that to be your outer boundary. And the other is to consider it a bad shield and take the interplanetary medium as your boundary. And that case is a little bit more complicated because the boundary of the interplanetary medium, the magnetopause, is actually not spherical. So your geometry is no longer exactly spherical. But basically the upshot of the whole of this whole thing is that we actually find that the results of our calculations are relatively independent to the exact shape of the outer boundary. So really, in both cases, you get the same answer for the relevant component of our signal. So our signal is actually pretty robust to the details of your environmental model. So in the pictures I'll be showing you for the rest of the talk, I'll just be showing the ionosphere as the outer boundary, but I'll show you why it's robust to the exact details of that outer boundary. So this, for instance, is what that corresponding picture would look like. So inside we have the Earth, which is a good conductor. We have some vacuum region outside of it, which is the lower atmosphere. And then we have the ionosphere surrounding that, which is also a good conductor. We can run through a similar Ampere's law argument to what we did for the cavity. So here I'm just considering the dark photon case. So if the dark photon is polarized, say, along the Earth's rotation axis, then this leads to some uniform effective current inside this the cavity between the ionosphere and the Earth. So again, we can consider some Amperian loop, which runs around the equator. And let's consider a corresponding Gaussian surface, which actually just hugs the northern hemisphere of the Earth, so it stays inside our lower atmospheric region. Again, we see that there's some current flux through this Gaussian surface, and so this leads to some magnetic field around the equator. And if you do the scaling out, you see it's precisely the same math as what I showed you for the previous Ampere's law argument. In particular, again, you see that we have this MR scaling where R is now the radius of the Earth. It's not the height of the atmosphere. In particular, you see that you could actually take the ionosphere to be as close to the Earth as you want. You could take H to be as small as you want, and this wouldn't change the argument at all. So it can't depend on the height of the atmosphere. You can also see that you can actually change the shape of the outer boundary as well, and this also wouldn't affect the argument. This is kind of why it's robust to the exact details of your outer boundary.
Oh, sorry.
Yeah.
I don't understand what the area is supposed to be the one that's embracing the northern hemisphere instead of the green. Why are we not looking at the area of the green around the equator?
You mean why did I choose? Like, are you saying just in this formula?
Yeah.
Why did I use that? Or
Yeah.
yeah, so I mean, I guess the actual A you would put here is like this cross-sectional area. So that would be like pi r squared as opposed to like 4 pi r squared. But either way, the scaling you get is the same.
But I thought the area within the Earth would not count because it's not a good conductor. So I mean, it is a good conductor, so it shows everything from the inside. So I thought we would just take the area of the green, excluding the area of the Earth.
Well, so the actual Gaussian surface that I've taken is entirely in the lower atmosphere. It doesn't go inside the Earth. So then I can evaluate the like surface integral all along that. And like at every point there is some like angle between the current and the surface. So there is some like angle you have to account for in that surface area integral, but it's equivalent to if you had just taken a cross section. Yeah. Yeah, but I guess the point is that I specifically chose the Gaussian surface to sit in the lower atmosphere precisely to avoid this type of like issue. Yeah. Okay, but yeah, that's a good question. Okay, so now I want to try to go through the derivation of this signal in a little bit more detail. In order to talk about that, I have to introduce vector spheric harmonics. So these are the analog for the scalar spheric harmonics you might have seen come up in like the hydrogen atom. But rather than being scalar functions, these are now vector functions on the sphere. And in particular, there are three of them, but they're still indexed by the same L and M that you're used to. L goes from 0 to infinity, M goes from -L to L. In the dark photon case, only the L equals 1 modes are going to be relevant. So those are what I'm showing you here, the L equals 1, M equals 0 modes. So roughly, you should just think of the Y modes as being radial, so they either point into or out of the sphere. These psi modes point up longitudes, and these phi modes point around latitudes. In particular, this phi mode is actually going to ultimately be the shape of the magnetic field signal that we're going to find at the end of the day. That's why, like on the previous slide, we were finding an equatorial pattern for the magnetic field. These pictures that I'm showing you are particularly for the M equals 0 case. The M equals plus or minus 1 cases will basically, the pictures will look the same except oriented along the X or Y axes instead of the Z axis. So basically, when I talk about these vector spheric harmonics, you should have these pictures in mind, just perhaps rotated at different angles. But importantly, like the scalar spheric harmonics, we can do, if we have any generic vectorial function on the sphere, we can decompose it into our different spheric harmonics, and we can project onto different vector spheric harmonics that we care about or don't care about in the same way that you would do with scalar spheric harmonics. Good, and for the argument I'm about to do, I need a little bit of vector spheric harmonic calculus just to show you how some of these things are related when you take derivatives of them. In particular, if you attach some radial dependence to them and then take the curls, these are the formulas you get. The exact formulas are not that important, but the things the two takeaways I want you to get from this slide are just that the curl of a phi mode, if you attach just a linear radial dependence to it, will just be a constant field, right? You can see if you attach a linear radial dependence to this, it's just a bunch of arrows pointing in circles. So that's a constant curl field. And then the other takeaway is that these Y's and psi's, their curls look like phi's. So if you want to get a curl-free field, you need it to be a sum of Y's and psi's. The curl of a phi is never going to be a curl-free field because there's nothing you can cancel it out with. So just the two takeaways are that constant curl fields look like phi modes, and curl-free fields have to be sum of Y and psi modes. Those are the only two takeaways you really need from this slide. Okay, so now we can actually derive the dark photon signal. So as I said, the dark photon sources some effective current. Because the dark photon just points in the same direction everywhere, then so does the effective current. It's just some uniform field. As we saw in the previous slide, a uniform field looks like Y's plus psi's. And in particular, because it can point in some arbitrary direction, then we want to sum, it can generically have contributions from each of the M modes, the M equals -1, M equals +1, and M equals 0 modes. Now, the crux of this argument is essentially just realizing that the electric field inside the cavity in the lower atmosphere where we sit should generically be small. And this is just because our entire cavity is sub-wavelength. So this is the case that I mentioned earlier, that we're only considering the case where the Compton wavelength is much larger than the Earth. And so this is just because the electric field deep inside the Earth, it has to vanish. Since the Earth is a good conductor, the electric field deep inside the ionosphere also has to vanish. And since there's just not that much distance between those 2 points, then the electric field in the lower atmosphere has to be relatively small.
So what mass does that correspond to?
10 to the minus 14 EV, I think, is the inverse of 1 Earth radius. We're actually going to be even lower just because of the frequencies that supermag probes. Yeah, so we're like 10 to the minus 17 or 18 EV. Yeah. Good. So that just means if we look at Ampere's law, we can ignore the electric field term, and then we just see that the magnetic field signal we're going to get is related to the effective currents from the dark photon just by taking the curl. So now we saw that the effective currents points in some uniform direction. And I said on the previous slide that the only constant curl, the constant curl fields are phi fields. So in order to solve this equation, we need B to have some phi shape. So this is precisely, this is what I said before, that the magnetic field signal we're going to get is going to have some phi shape, meaning if the dark photon is oriented along the Earth's rotation axis, then the magnetic field we get is going to point along latitudes. Now, of course, this equation here doesn't fully determine B. I can, of course, add any curl-free component to B, and it will still satisfy this equation. So generically, the boundary conditions will determine what this curl-free component is. It may not just be this phi component, but as I mentioned on the previous slide, curl-free fields are made of y's and psi's. They're not made of phi's at all. And so what this means is that regardless of what the boundary conditions are, this is always going to be what the phi part of your answer looks like. The y's and psi's may change as you change the boundary conditions, but the phi part will always be precisely this. So this means that, for instance, if I project specifically onto the phi components of the magnetic field, then I've completely eliminated any dependence on my boundary conditions. And so then I don't have to worry about these complicated questions of how does the ionosphere act and such. So this is the magnetic field signal that we're going to be looking for the dark photon case. And there's one subtle caveat, which I haven't talked about, which is that I didn't account for the rotation of the Earth. The calculation I had done up until now was all in inertial coordinates. However, the Earth actually spins and our magnetometers sit on the Earth, so they're also going to spin around. So all that basically means is that that's going to correspond to just some coordinate change, where rather than caring about some points which is fixed in inertial space, we want to care about points which co-rotate along with the Earth. And it turns out that the only way that actually changes the answer is it just adds this slight frequency shift to the different modes. So in particular, this frequency shift will not, it won't shift the m=0 mode. It'll shift the m=1 mode one way and the m=-1 mode the other way. So this will give you side bands for your signal. You'll expect some signal at the mass of the dark photon, and then some at +1 over a day and some at -1 over a day. Great. Okay, so that was the dark photon signal. The axion signal, the derivation proceeds pretty similarly. The one important difference between the axion and dark photon cases is that the axion needs a static background magnetic field. Luckily for us, the Earth quite famously has a static background magnetic field. And so we're going to parameterize the Earth's geomagnetic field using this IGRF model, which is basically just a multipolar expansion of the Earth's magnetic field. These CLM coefficients are just the coefficients of the multipolar expansion, and the IGRF model gives you the values for those. As you know, the Earth's magnetic field is mostly dipolar. So this L=1, m=0 term is going to be the biggest one, but there will be some small contributions from other terms. And also the Earth's magnetic field actually does drift slightly over time. So these CLMs really do have some time dependence to them. The IGRF model gives us values for these at 5-year intervals and then just tells you to linearly interpolate between those. So that's what we do. And then the actual derivation proceeds pretty similarly. Given this magnetic field that in the presence of an axion, this will source some effective current. It turns out that this effective current is also going to look like Y's in size. Wait, was there a question? Or, oh, okay, never mind. Yeah, so like on the previous slide, the effective current will also be some combination of Y's in size, but it'll be a different combination. And it turns out that the magnetic field signal that that ends up correctly solving this will also be in the form of phi fields, kind of like the axion case. Or sorry, kind of like the dark photon case, but with slightly different coefficients. And again, like the dark photon case, this fully determines the phi piece. There can be some additional curl-free piece, but that's going to be entirely Y and psi mode. So if we take our magnetic field signal and just project onto phi modes, then we get an answer which is entirely independent of boundary conditions. And this entire calculation also has been done. Oh, is there a question?
No, I'm just checking if there's any question. Yeah, I don't see any question.
Oh, okay. All right.
Yeah.
I thought I heard somebody trying to talk. Yeah, so this calculation has actually entirely been done in co-rotating coordinates because the Earth's magnetic field rotates along with the Earth. So we've already accounted for the Earth's rotation here. We don't need to do an extra step like we did on the last one. Great. Okay, so this is a summary of all the important properties of our signal. It's, as I mentioned, it's some observable oscillating magnetic field at the Earth's surface. Importantly, it scales with the radius of the Earth, not with the much shorter height of the atmosphere, which means it's big. It's something we can actually detect. Oh, sorry. It has a particular global spatial pattern, these phi modes, which point around latitudes. Another way of saying that is that it's spatially coherent. So the field in London and the field in Tokyo and the field in San Francisco are all related. In addition to being spatially coherent, it's also temporally coherent, like most dark matter signals. So if you Fourier transform it, go into frequency space, it should be sharply peaked in frequency space with a Q of 10 to the 6. These spatial and temporal coherences combined give you a lot of statistical power and make it a lot easier to look for this signal. And then finally, this signal is robust to the particular environmental details and how accurate the model I showed you a few slides ago actually was, because these phi LM components don't really care about the boundary conditions. Okay, and while the dark photon and axion signals look very similar, there are a few subtle differences that it can actually let you distinguish between the two of them. First off, the dark photon signal only uses the L equals 1 modes. In particular, it can be any linear combination of those 3 L equals 1 modes. But the axion signal, because that's determined by the Earth's magnetic field, which is mostly dipolar, but not exactly dipolar. The axion field will be mostly an L equals 1 mode, but it'll have some contributions from higher modes as well. But it'll be one particular linear combination of all of those modes. In addition, because of the rotation of the Earth, the dark photon signal got these sidebands. So if you Fourier transformed, you'd see. Is there a question?
It's someone clearing that throat. I have their mic on. So
Yeah, there's my.
Okay.
that's what it is.
All right. Yeah.
Okay, just tell them in the chat.
Good. Yeah. So in frequency space, you would see some spike both at the dark photon mass, but also at plus or minus 1 over a day. Whereas in the axion case, you would have no such sidebands. You'd only see a peak at the axion mass. And then finally, the coherence properties of these two signals are slightly different. So as we'll see, we have data from longer than the coherence time. So over the course of our experiment, the axion or dark photon will actually change. The dark photon, for instance, will change its direction and amplitude and phase. And what this means for the signal is that the amplitude and phase of the signal can change, but also the orientation can change because that's determined by what direction the dark photon is pointing in. In the axion case, however, the axion doesn't have a direction. Instead, the orientation of the signal is determined by the Earth's magnetic field itself. So over many coherence times, the amplitude and phase of our signal will change, but the actual shape, the orientation of the signal will not change. Instead, the orientation will slightly drift as the Earth's magnetic field drifts, which is a much, much slower time to scale.
So does that mean you're making the assumption that the dark photons are completely polarized? Or do you not have to rely on that assumption?
Well,
Yeah,
I mean, in the vicinity of the Earth, you should still be able to just treat it as having some particular polarization.
Yeah, I'm not
Yeah.
sure, because if you produce dark photons with some production mechanism that produces those left-handed and right-handed simultaneously with the same amplitude, then I don't know if you can still have any coherence time with polarization. I thought that would just be completely unpolarized.
Well, I think it would be unpolarized like over many coherence times, but I think within a coherence time, like a coherence time is the duration over which the like direction is going to be fixed. Like when you talk about like light being unpolarized, I think that's because you're talking about it over like many oscillations of the light when it's not maintaining some coherent polarization. Yeah, I think that should be correct. Okay, are there any other questions actually up until this point? Okay, cool. Then I'll round things out by talking about how we actually detect this and our analysis of the SuperMag data. So as I mentioned, we take advantage of data from the SuperMag collaboration. This is a collaboration of over 500 ground-based magnetometers. You can see their distribution over in this picture here. They've been taking data over a 50-year time period. These are the number of active stations which have been reporting data over the course of the past 50 years. And the data set that we're going to be using uses a 1-minute time resolution. Now, I won't go into obviously the gory details of the analysis, but to sort of give you a flavor for what some of the things that make this analysis a little bit difficult are, I'll just kind of run through what we would have liked to do, why that's hard, and what we actually do. So I guess the naive thing you would like to do is, first off, you'd like to project onto these phi modes, as I've been talking about, so we can eliminate the other contributions which are dependent on the boundary conditions. Then we would just like to Fourier transform, go to Fourier space, and what we should see is just some nice single frequency peak at the mass of the dark photon or axion. But these are difficult for a few reasons. One, projecting onto these vectorspheric harmonic modes is a little complicated. First off, because the noise in our different stations tends to vary. So for instance, if you were projecting onto the L equals 1, M equals 0 mode, then what you would have done was upweight all the stations near the equator, but downweight the ones near the poles. But if you happen to have a noisy station near the equator, maybe you don't want to upweight that. Or if you have a cleaner station near the poles, maybe you would want to upweight that. In addition, these the noises between the different stations can actually be correlated, leading to some complicated effects. You can also see that they're not really uniformly distributed around the sphere. So it makes taking this projection a little bit tricky. In addition, Fourier transforming the signals from each of these stations is a little complicated because the stations turn on and off a lot. You can see from this picture over the course of the 50 years, many turn on over the course of 50 years and some of them turn off at certain times. So just taking you don't have one consistent time series for a lot of these stations, and that makes taking a Fourier transform with them difficult. And then finally, looking for just a single frequency peak wouldn't be quite correct because the total time, the total duration of our experiment in many cases is going to be longer than the coherence time of the dark photon or axion. And this means, sorry, I think I clicked something. Just trying to print. Okay. Oh, there's a chat question.
Oh, no.
Oh, I see. Okay. Gotcha. Good, yeah. So because the total time is longer than the coherence time, this would mean in frequency space, you would actually see some width to your peak. So it wouldn't just be a single frequency. Okay, yeah. So this is a rough overview of what we actually end up doing. So first off, in order to create some time series, which actually has values at all times, we take all of our stations, we combine them into just a few time series. So we actually have data at any given time. We do this combination both by weighting by the vector spherical harmonic modes that we're interested in, and also by the inverse noise, so that we're upweighting stations which are cleaner and downweighting stations which are noisier. Of course, this would do complicated things to an actual dark photon signal. So we do the same process on a dark photon or axion signal to see what we should be looking for. And then to deal with the fact that our peak should have finite width, the fact that our total time is greater than the coherence time, what we do is we divide our total time series into separate chunks, each of which is roughly a coherence time. So within each of those chunks, you can just look for a single frequency peak as if the signal was entirely coherent. And then you just combine the results incoherently. In particular, we use a Bayesian framework to derive a posterior for these coupling parameters by combining these incoherently. So this is roughly what the results of our analysis look like in the dark photon case. So on this horizontal axis here, you have the mass of the dark photon. On the vertical axis here, you have the kinetic mixing parameter. And shown in blue is our analysis based on the supermag data. It shows up as a band because of just bin-to-bin bin-to-bin variations. So we also show this smooth version of the limit in light blue here. You can also see some other astrophysical constraints shown in various colors here. These are mostly from various heating bounds of different astrophysical objects. You'll note that all of the astrophysical bounds are exactly parallel. They all have this 1/m slope here. This is just because of what I've been telling you, that most dark photon effects will always scale with the mass of the dark photon. So they'll always appear as like epsilon m. This is why these all have the same scaling. You'll notice that our bound actually scales slightly faster than these other bounds. This is because in addition to the epsilon m scaling of the signal, our noise also gets better as we go to higher and higher frequencies. So in particular, if we could go even further to the right here, you might expect that we could actually beat some of these astrophysical bounds. We actually get cut off around here. This is just because of the finite time resolution of the supermag data set. This is roughly 1/a minute, and as I mentioned, they use a 1-minute time resolution, so we can't go any further to the right with this data set. This is a similar bound for the axion case. So now this vertical axis here is GA gamma. Sorry, is there a question? Oh, okay, yeah. This is the axion photon coupling. We're also showing bounds from the CAST helioscope and bounds based on the supernova 1987A. Again, as you go to higher and higher masses, now the signal is not changing as you go to higher masses, but our noise is still getting better, so we do improve. And if we could go to even higher masses, we might be able to beat out CAST and supernova 1987A, although we're already putting bounds which are quite comparable to CAST. Great, so where do we go from here? Well, it actually turns out that supermag does have a higher resolution data set. And as I mentioned, if we use this higher time resolution, then that will allow us to go to higher masses on these plots. If the noise continues kind of the way we've been seeing it so far, then we can see our bound actually scales better than a lot of the other existing bounds. So we might be able to reach new parameter space with this 1-second data. So we're actually about to undertake the analysis of this 1-second data. There are also other ways you might imagine improving this analysis. For one thing, we didn't do any kind of noise modeling. We just took everything we saw and treated it as noise, but maybe if you understood some of the the sources of this magnetic field noise, you might be able to eliminate some of these backgrounds a little bit. Of course, maybe a more sophisticated statistical analysis might give you better results. It's kind of a sort of an open question whether or not better magnetometers might help. The magnetometers which Supermag is using are not the state of the art or anything. And of course, more data is always better, especially data at higher frequencies. So in summary, I demonstrated a novel mechanism to detect ultralight dark matter using the Earth as a transducer. It takes advantage of the natural conductors around us rather than man-made conductors in a lab. Importantly, our signal is not suppressed by the small height of the atmosphere, but rather by the large radius of the Earth. This means that it's something sizable that we can actually detect. It's both spatially and temporally coherent, which give you a lot of power when searching for this signal. And also it's robust to the exact model of the near Earth environment. So the precise details of the ionosphere are not super important for our signal. I showed that we set competitive balance for both dark photon and axion parameter space, and look forward to the 1 second analyses coming out soon. Yep, that's it. Thanks.
What is the event rate? How did you expect?
Well, so this is like in the low mass range where we're treating it as like a classical field rather than as like discrete events. Like this is not like a WIMP detector where you would
Right.
see like discrete events.
So why isn't this then just built into what we see as the magnetic field on Earth anyway? How do you pull that apart?
Good, yeah. So that's where like the spatial and temporal coherence would become very useful. So like normal magnetic fields, the normal Earth's magnetic field, you'd see like a bunch of random different noise in different places all around the Earth. And it's not like that coherent, not that temporally coherent versus like this noise or this particular signal would appear as a very particular pattern, everything pointing in the same direction, and at like a precise frequency. So it would be like an exact sinusoidal signal. Not exact, but very close to a
So
sinusoid.
you're looking for a coherent part on top of sort of this random background? Or-
Yeah, yeah, that's exactly what we're looking for.
And the other question, for the photon case, is there a reason that you did it through mixing in the mass rather than in the kinetic term?
Good, yeah. So as I mentioned, there are a few equivalent ways of writing the dark photon Lagrangian. They are the way you're thinking of writing it is equivalent to this way. Like so basically, yeah, rather than having this term, you could have like an epsilon FF dual term. There's a FF prime term. And then just by redefining your fields, that will change it into this form. But this form makes it more apparent, for instance, that
I don't think it just changed. Well, I could be wrong, but I mean, don't you actually get a mass for the photon this way? I mean, it's going to be small, but probably allowed. But doesn't that give you a mass for the photon?
No, it shouldn't. Like one of your modes will still be exactly massless.
Well, it's a 2x2 matrix, and you got your off diagonal terms and one diagonal term. That gives you. That's just like for neutrinos, you're going to get. Be a little bit like a seesaw if you want, but
Yeah. Oh, okay.
You get a photon mass this way.
It might be. Yeah. It might be like higher order. It might be epsilon squared.
It's definitely epsilon squared
Yeah.
times ma prime.
Yes.
And it's allowed, I think, because you're taking ma prime to be very small anyway, and then
Yeah.
epsilon squared times that, it's probably, well, it's certainly below the experimental limit on the
Yeah.
photon mass, but it still means you've got, electric charge down conservation at some level, right?
Yes. Yeah. I think that is true.
And you don't get that if you do the regular kinetic mixing, I think.
Yeah, okay, yeah, I think you're right that these are only the same up to like order epsilon squared, or sorry, up to order
Okay.
epsilon. But yeah, I mean, we're taking epsilon to be very small, so it shouldn't make a huge
It's not
difference,
that
but yeah.
small. I mean, 10 - 3 or 10 - 4 is not that small, but you know, as I said, I think the photon mass is epsilon squared that you get out of this, and
Wait, actually,
it's epsilon squared times NA prime.
yeah, no, I think you're
Or maybe
probably
not.
right.
Maybe it is just epsilon. Because your mass is square root of epsilon. So it's probably epsilon times NA prime,
Uh,
which is, you know, if
yeah,
NA prime, well, if NA prime is 10⁻14, then you might have issues. But if it's 10⁻17, which is what I thought it was in the last figure,
yeah, no, in the last figure, it is like 10 to the minus 17 or 10 to the minus 18.
yeah, then you're safe. But it's, you know, it's not that far from the experimental limit on the photon mass.
Yeah. Um. Sorry, I'm just trying to think through the calculation. It's like, there might be a chance that it is exactly massless, but I think probably you're right that it is like epsilon squared.
Epsilon. Because,
I mean, yes, I like epsilon squared m squared, which would be like epsilon m.
right, if it's
mass.
epsilon, yeah, but epsilon MA squared, the mass, well, it depends what you're diagonal, it doesn't matter what you're diagonalizing, but it would be, in the mass matrix, it would look like square root of epsilon times NA prime as your off diagonal element, and then it would go as epsilon. Just think of just the neutrino mass matrix for the seesaw.
Yeah,
That's
yeah, no, I,
That's
I
like
think
your
you're right.
direct mass, right? The epsilon is your direct mass, and your MA prime is your Majorana mass.
Yeah,
And you have 0 for the left-handed direct.
right,
mass.
yeah. Yeah.
But if
yeah,
MA prime is small, it's, as I say, it's not a problem, but, you know, so I don't know what other, but it might leak into something else. It's not a problem in the mass of the photon. Which is, I think, like 10⁻18 EV.
Yeah, you're saying like current bounds for,
Current bounds on
yeah,
the
are like
photon
10 to the
is
minus
about
18.
10⁻18.
Yeah,
So
exactly. So,
epsilon times, so all you need is epsilon times MA prime to be less than that.
right. And like, we're already working with MA primes, which are less than that.
Right, so,
Yeah, I mean, so there are like constraints on dark photon parameter space from like Coulomb, like just Coulomb force experiments. And probably this is where it would come in, but those, I think that those constraints are a good deal, like several orders of magnitude higher. Like, I think they're more like 10 to the minus 10 EV or something like that. Yeah, whereas I think that the argument you're making is really that those would still be relevant at like, 10 to the minus 16 or whatever.
yeah.
Yeah.
It's just not, because as I say, normally you see it as epsilon times F prime.
Right, yeah, and I mean, really like that is really what we are imagining. This is just like another way of writing it, which is equivalent at order epsilon. We've basically just ignored order epsilon squared terms. But yeah, those terms should be there.
Other questions?
The 1 second analysis, which is so
Well, that will basically just allow us to go. Yeah, it'll just allow us to go further to the right on this plot, assuming that we get a comparable bound over here.
It'll be better with that.
Yeah. So if we can go further over here, then I think there's some open parameter space we think we can get to down here. And in fact, I mean, just based off the size of the data files, which is obviously not a good way to measure these things, but like the 1 second analysis does seem to be a bigger data set than the 1 minute analysis. So it's possible that even down here, the bounds will improve slightly just from having more data. But at the moment, I'm not totally sure.
So if you had infinite time resolution, this would not go on forever, right? It would just go all the way up to 10 to the minus 14 eV.
Yes, yeah, exactly, because that's where the Earth.
But you don't expect the scaling to change all the way until 10 to the minus 14 eV.
No, yeah, it should continue all the way down there. To the extent that you believe the Earth model that we've written down. And we think that the Earth model is probably pretty convincing all the way down to there, but they're I mean, there's these subtleties with the ionosphere that around 10 to the minus 16 eV or something, you get to a point where if you don't believe the ionosphere actually shields you, then the distance between the Earth and the furthest edge of the magnetopause might actually be at the point where MR is about 1. So M times that length might be about 1. So there are parts of that range which might be a little bit hairy, but I think for the most part you should believe the signal up to 10 to the minus 14 eV.
Yeah. Okay, thanks. Any more questions? All right, if not, then let's change the speaker again.